Welcome back. In our last video we went through the convolution integral. We went through it step by step, graphically showing the inner workings of the convolution integral. If you missed it, it is highly recommended that you watch that one first, but no worries if you wish to stay and watch this one. So in this video we will be going through a worked example of a water tap filling a bowl. We hope that this example will further solidify your graphical understanding of the convolution integral. To recap the convolution integral, the response of a real system at time t is the convolution of the input signal with the transfer function. Graphically, the input signal is mirrored and then slided along and then multiplied with the transfer function, taking the area underneath the resulting curve of this multiplication gives us the convolution. Our worked example will be a tap filling a bowl, whereby the input signal f of t is the flow of water from the tap to the bowl. The output response h of t is the water depth level of the bowl. The transfer function g of t is how the water level of the bowl is influenced by the incoming water. As this is a simple bowl, the transfer function will be constant. You can make this more complicated with leaks, plug holes, siphons, etc., but we will be sticking to the simple bowl. So let's draw our transfer function g of tau, which is a straight line. We can draw a straight line like this. We'll give it some arbitrary value because it's constant, but in this case let's just say it's 1. For our input signal, let's say that our hand turns the tap on for a while, then off for a while, then on, and then off. This will be 2 input pulses. We can draw 2 input pulses like this. For f of tau, so the first input pulse will look like this, with some width for being on, then we turn it off, we leave it off, then we turn it back on again, and we leave it on for a bit, then we turn it off. To apply convolution to this, in the same way that we did in the previous video, we need to first reflect the input signal, then shift it, and then multiply the input signal with the transfer function. Then we need to find the area underneath this multiplied function between the times 0 and t. So reflecting and shifting the input signal will look something like this. Now then, we need to multiply f of t minus tau with our transfer function. So to multiply f of t minus tau with our transfer function, in this case, it looks pretty much the same because this is a constant and this is of this shape. So we draw something like this. Which is effectively these bits multiplied by that, which is equal to these bits, and then these bits at 0 multiplied by that is equal to 0. So to compute the response of our system at time t, we take the integral of this multiplied function between 0 and t. Now this is effectively the same as taking the area in this region. So now I'm going to plot the response of our system, h of t, for all time t. What we did just now was find the response of our system for a single point in time. So what we did was find the response at this point in time. So the area underneath this curve will, let's say it will appear here. As we shift our input signal along and keep multiplying it with our transfer function, which is a constant, we will end up with the same shape but shifted along. The only difference here is that the area between 0 and the shifted along more t will be larger. In fact, in this case it will increase linearly. So up until this point in our plot of h of t, we will get a linear relationship from the very beginning of our system to the end of our first input pulse. For this next bit, the response is actually going to flatline, because as we shift the input signal along, the multiplied functions are not really going to change shape much because the transfer function is constant. We are going to keep the same area underneath this curve up until we reach the next input pulse. So we're going to draw something that looks something like this. And as we've reached the next input pulse, the area underneath this curve is going to increase linearly, just like the previous pulse did. So we're going to get something that looks like this, a linear increase, up until the end of the pulse. And again, the same thing again applies from here, or the same logic applies from here like it will do here. So what have we just shown? We have shown how a water bowl fills up when you turn the tap on and off twice. You can see that here as you turn the tap on, the water bowl level increases linearly. Then as you turn it off, the water level in the bowl stays the same. Then when you turn it back on again, it goes up linearly again until you turn it off, and then you're left with a fixed level of water in your water bowl. To conclude, we have shown that the convolution integral can be used to work out the response for simple situations. In fact, it can be extended to more complicated models, which we might explore further in another video. I hope you enjoyed watching this video and you found the content enlightening. If you found my work helpful, please press the subscribe button to see more videos in the future. Thank you for listening.